Okay, so this will be Lecture 3, Part 4. So essentially Chapter 3, Part 4 of the text. And this regards the law of signs. So we'll talk about what that means. So consider this illustration of the triangle I have drawn here. All right, so I've labeled the angles with uppercase letters and the length of the sides of the triangle with lowercase letters. And I've shown the altitude, the height of the triangle. And so we have this illustration. And so in triangle ABC, the law of signs stipulates this. For triangle ABC, that the sine of A divided by the length of the opposite side is equal to the sine of B divided by the length of its opposite side, which is equal to the sine of C divided by the length of its opposite side. All right, so we have this important relationship between the lengths of the sides of a triangle and the sines of the angles of the triangle. All right, and so the proof is not too bad. We use the results from Lecture 3, Part 3 to know that we know that the area of the triangle ABC is 1/2 AB times the sine of the angle between the two sides. So 1/2 AB times the sine of C is equal to 1/2 AC times the sine of B, which is equal to 1/2 BC times the sine of A. All right, so those are all the area formulae for the triangle. Now, so if I take these equalities and I equal them line them up like this, and then if I divide through every term in this chain of equalities by 2 over ABC, the result follows. Okay? So multiply everybody by 2 over ABC, and you'll get the result. So it's a pretty easy result to obtain. But interestingly enough, the types of problems that come from it are somewhat difficult. So we have the next class of problems we consider, and I'll paste it in here from the lecture notes, the idea of solving a triangle. Okay, so solving a triangle. So let me configure a page for you. I don't know what's going on with my computer. This is so slow. Must be the time of day. The internet gets slow this time of day. Okay. So consider this class of problems here. Look at this first triangle. All right, so when we solve a triangle, what we want to do is we want to compute the measures of all the angles and the lengths of all the sides. So in this case, the information given is the measure of angle C is 25 degrees. The measure of angle A is 20 degrees. And we want to find, say, the measure of angle B as well as the lengths of the three sides. And we're given that the length of side C is 80.4. So knowing that the sum of the measures of the three angles of a triangle is 180 degrees, we can easily get angle B just by subtracting 20 plus 25 from 180. So angle B has measure 135 degrees. And then we can invoke the law of sines. So sine A over A is equal to sine B over B, which is equal to sine C over C. So A then is equal to what? C times the sine of A divided by, let's see, is that right? C. So let's check that. All right, so we have sine A over A is equal to sine C over C. So A then would equal to C times the sine of A divided by the sine of C. Okay, so that works. All right, so we know what C is. We know what the sine of A is. We know what the sine of C is. All right, so make the substitutions. So we have 80.4 times the sine of 20 divided by the sine of 25, and then when you solve that on your calculator, make sure your calculator is in degree mode, and you'll get the length of side A is 65.1. And then by a similar algebraic process, you can get B being 134.5. Okay, so this is case one. In this case, essentially the angles that we're dealing with are acute angles, so there are no major issues here. In the second case, though, something different happens when we try to solve a triangle. So look at this particular triangle. We have the measure of angle A is 45 degrees. The side opposite, in other words, lowercase a, is 7 on the square root of 2, and B is 7. All right. So using the law of sines, we would expect the sine of A over A is equal to the sine of B over B. And so we can solve for the measure of angle B ostensibly. So the sine of B is equal to B sine A over A, and then when the result follows, we get that the sine of angle B is 1/2. So the sine of what angle is equal to 1/2? Okay, well, the sine function, as you know, is a multi-valued function. So if we recall from our table from lecture 3.2, this means that angle B could be 30 degrees or 150 degrees, because we know the sine of 150 degrees is a half also, okay? Because the reference angle for 150 is 30, and the sine of 30 is a half. And we know that the sine, 150 degrees, is in quadrant 2, and the sine is positive in quadrant 2. So we have a multi-valued function for the sine function. But angle B, of course, cannot be 150 degrees. You would have to reject that solution because angle A is 45 degrees, and 45 plus 150 is 195, and of course you can't have two angles summing to 195 degrees in a triangle. All right, so that means angle B has to be 30 degrees, and so then you can get angle C, which is 105 degrees. And so now we can compute the length of side C, the remaining unknown for this triangle, by letting B equal 7, taking the sine of angle C, which is 105 degrees, divided by the sine of 30, and so C is 13.5. So we've solved the triangle. Okay. All right, so you have to watch out for those kinds of details. This is basically an example of a constraint. So the third case is a little more difficult. There are 4 cases total, so we'll do the third case. I'm just reading what that's going to be about. Okay, so let me paste a note from the lecture notes and copy it. Okay, so consider triangle ABC. Let's see, which triangle are we working with here? Let me see, hang on, there's an error in the drawing here. Oh, okay, so in this problem, we want to solve triangle ABC if angle A is 43.1 degrees. The length of side A, okay, where's my pointer? So the length of side A is 186.2, and the length of side B is 248.6, okay? And so the measure of angle A is 43.1 degrees. And so ABC, okay, so what is triangle ABC? So let's proceed to solve it. Now, assuming that B1 is B, okay, is vertex B, angle B. So let's assume that that's angle B, okay? So the sine of angle B would be B times the sine of angle A divided by A. So solving this, plugging in the numbers, okay, using our calculator in degree mode, we get that the sine of B is 0.91225. Okay, so that means that if we take the inverse sine of both sides, okay, assuming that we can, although it's a bit strange at this moment in time because the sine function is not one-to-one, but assuming that we could take a slice of the sine function that's invertible, we would see that the measure of angle B1 is equal to the inverse sine of 0.91225, which is 65.8 degrees. So an acute angle. Now, we could potentially have angle B being this angle, an obtuse looking angle. Okay, in which case we would have, okay, well, before we go to this step, now we have, we'll go to this step. Okay, there's a potential that B could alternatively be 180 degrees minus 65.8. In other words, we could have angle B being a quadrant 2 angle. It's possible that angle B could be quadrant 2. So because angle A is a quadrant 1 angle, it's possible that angle B could be a quadrant 2 angle. So to solve for angle C1, so angle C1 would be the angle affiliated with, if we go with B1. So suppose we could have C1 being this angle then. So in this case, angle C1 would be 180 minus the sum of those A plus B, so that would be 71.1 degrees. And then you could solve for the length of side C1, which is here. Okay, that would be C1 would be the length of the side associated with angle C1, and you'll get, once using the law of sines, you'll get this number 257.8. Okay, so in the other case, suppose we opt to use angle B2, which was the obtuse angle, okay, the quadrant 2 angle. So then angle C2 would be found using this, the sum of the three angles equal 180 degrees. So then angle C2 would be 22.7 degrees, and that means you would have an alternative for length of side of C. We'll call it C2, which is 105.2. So this is called a kind of an ambiguous case, well, not an ambiguous case, a case where you could have multiple solutions when solving for a triangle. You have to leave open the possibility that if you're not given sufficient information, then you have to account for all potential values that one of the angles could take on. The angle could be in quadrant 1, or could have a terminal side in quadrant 1 or a terminal side in quadrant 2. So be very conscientious of how you manage these kinds of problems. In this case, the omission of information in the problem statement, you'll have to extend your analysis. Okay, and so now we have the fourth case. Which one is that? All right, so if we're given the length of two sides of a triangle, let's see, and the measure of an angle, okay, that's called the side-side angle case. Okay, actually case 3 is called the two-solution case. So what we've seen is we have a one-solution case. That was case 2. What was case 2? Case 2 was, well, case 1 was the one-solution case. Case 2 was a one-solution case. Case 3 is a two-solution case. Now, case 4 is a no-solution case. Okay, so let's see what that would be like. So suppose I ask you to solve triangle ABC. So this will be case 4. Case 4 here. If the measure of angle A is equal to 42 degrees, A is equal to 70, and B is equal to 120. Okay, so we'll call this case 4 an SSA, side-side angle. You're given SSA information, side-side angle. Okay, so now we go ahead and commence the computation. So we'll have sine of A over A is equal to the sine of B over B. All right, so so the sine of B then would equal to B times the sine of angle A divided by A. Okay, and so plugging in the numbers, B is 120, and the sine of 42 degrees divided by 70. Okay, so the result using your calculator will be in radians. So we'll have the sine of B is what? So when you calculate that, that would be 120 times the sine of 42 degrees divided by, what's that, 70? 70, which is equal to 1.14. All right, so now recall the range of the sine function. We know that the sine function is always between -1 inclusive and 1. So if your sine function is pointing to 1.14, that can't happen. The sine can never be greater than 1. So thus we have no triangle. So in this case 4, no solution. This is an impossible triangle to draw. This is not a triangle. Okay. All right, so let's do 2 word problems using the law of sines. So I'll paste them from the lecture notes. We'll work through them. This one is an aviation problem here. Okay, so in this problem, we have a pilot is flying over a straight highway. He determines the angles of depression to 2 mileposts. Okay, so the mileposts, they're not shown very well in this illustration. So milepost here, let me check that. Let me check the mileposts. Okay, so here's a milepost at point A, and then here's another milepost that doesn't have a label. All right, so he determines the angles of depression to 2 mileposts 5 miles apart. So the difference between these posts is 5 miles. All right, so we've got that distance, 5 miles. Okay, and the angles of depression, of course, would be formed between the line of sight of the airplane with the ground. All right, so one angle of depression is 32, the other one is 48. So we want to find the distance of the plane from point A. So we want to find this distance right here. Okay, so how do we find this distance? Well, one way is we can use the law of sines. So we know so we can say, well, let's let x be the distance from the plane to point A. So we'll call the length of this side x. Okay. So now we can also find the measure of this angle. Okay. So the measure of this angle, let's just call this angle theta. All right. So theta is equal to 180 degrees minus 32 plus 48. And that's 100 degrees. Okay? So we have the following result. let's see. Now, we also have a transversal, right? So we know the measure of this angle. Let's call it gamma. Because we have a transversal, we know from geometry, let's see here. We have theta, we have 48 degrees. So this is a 148, so we know that the measure of this angle is 32 degrees, right? And let's see here. So that means gamma is equal to 32 degrees. And so this angle right here we'll call beta. So beta must equal to 48 degrees because this angle is 48 degrees and we have alternate interior angles of a transversal across two parallel lines. So that comes from geometry, high school geometry. Okay, so beta is 48 degrees. Okay, so let's see here. So we have a relationship. So we have x over, let's see here. We can use the law of sines here, right? So x over sine beta must equal to 5 over sine theta by the law of sines. So now we can solve for x. So x must equal to 5 sine beta divided by the sine of theta. Okay, and so that would equal to, when you plug it in using degree mode in your calculator, that would be 3.77 miles. Okay, all right. And so the question, okay, so part B is find the height of the plane, the elevation of the plane. So that would be that side, okay? Well, we know x, we know gamma. So let's see here, h. So we know that the sine of gamma is equal to opposite, which is h, over x. Okay, and so the sine of 32 degrees is equal to h over x, which is 3.77 miles. Okay, and then solving for h, h is about 2 miles. So about a little less than 11,000 feet would be the elevation of the plane. Okay. All right, so let's do one more word problem for section 3.4. Let me paste it in the whiteboard. Okay, so in this problem, a tree on a hillside casts a shadow 215 feet down the hill. All right. If the angle of inclination of the hillside is 22 degrees, as shown in this illustration, to the horizon, okay. Let's see. To the I'm sorry, not to the horizon, but to the horizontal, and the angle of elevation to the sun is 52 degrees. Find the height of the tree. Okay, so what's implicit in this problem is the angle of inclination and the angle of elevation are measured from the endpoint of the shadow. Okay, so right here is the endpoint of the shadow. And let's see, the shadow length right here is 215 feet. Okay, and so we want to find the height of the tree. And we'll assume that the tree is growing perpendicular to the ground. Okay, perpendicular, that is, to the flat ground. Okay, so this is a perpendicular. So this is perpendicular this way. Okay, so knowing that, so we can find this angle right here. So this is the angle subtended by the top of the tree in the sun's ray. We'll call that A. So angle A would be what? That would be 180 minus, okay, now this would be a 90-degree angle here. So it would be minus 90 minus, okay, let's see here. Hang on. Yeah, oh, I'm sorry. Yeah, right. So it would be minus 52. So that means the measure of angle A is 38 degrees. Okay, so now, can we use the law of sines? So sure. So now we consider, now that we know the measure of the angle, we know that the measure of this angle is 30 degrees right there. That's a 30-degree angle. We know this is a 38-degree angle. And we know what else? And we know that, can we use something else? We know 215 feet. So we know, what else? Okay, yeah, we know the length of this side. That's 215 right there. Okay, so we have enough information to use the law of sine. So, so we have the sine of 52 degrees over h is equal to the sine of 38 degrees. Let's see, sine of 52. Wait, let's see, sine of 52. Wait, is that the right angle? No, not the sine of 52. The sine of 30, I beg your pardon. This angle is 30 degrees. Sorry, we're talking about, I was looking at the wrong triangle. We're talking about this triangle right here. Okay. And the length of this side is 215, so the angle, this angle right here is 30 degrees. So that should be 30 degrees, sorry. So the sine of 30 degrees over h is equal to the sine of 38 degrees over 215. Okay. So h then is 215 times the sine of 30 divided by the sine of 38 degrees. And so that turns out to be 175 feet. All right. So that is the law of sines. We've got word problems, and we have solving triangles in 4 different cases. And we have the formula for areas of triangles. So quite a bit done in this section. So I will end the video lecture with this particular section. And so please start working on your WebAssign. And we have one more section to go for this chapter. So, and that, of course, will be the law of cosines, which is very, very important, especially to navigation in global positioning systems. So that's it for now. 3-4 in us next.